Energy in a pendulum. You recall when we were talking about the energy in a mass spring, it was a combination. So let's see, let's write this down. Mass spring. We said we had, well, obviously there was a spring, so it had an EPE. And as it went by the equilibrium point, it had KE. So it was EPE and KE. Now for a pendulum, it's a little bit different. It's still moving. That pendulum is swinging back and forth. So we do have KE, kinetic energy, 1/2 mv squared. But as it moves, as it's moving back and forth, we notice that it also is gaining some height. So if it has height, it has gravitational potential energy. Gravitational potential energy. So a different type of potential energy. Potential energy, otherwise known as GPE. M is mass, and that's in kilograms. G, you'll recall, is just that acceleration due to gravity, which is 9.8 meters per second squared. And H is the height that pendulum swings up, and that's in meters. At any moment, the total energy of the system is a combination of those two energies, GPE and KE. Here's the two equations for GPE and KE. So the total mechanical energy, like when we're talking about a mass spring, is constant. It just varies between GPE and KE, GPE and KE. Here's our first problem. What is the total energy of a 1 kilo? So we want to know total energy. And remember, the units are joules for energy, of a 1 kilogram pendulum. So its mass, they're telling us, is 1 kilogram. If its height at its maximum amplitude, so we can call its height 0.2 meters above its height at equilibrium. So we have E total is a combination of its kinetic energy and its gravitational potential energy. And we know when that pendulum swings back and forth, when it's all the way at its maximum point here, it's all GPE. It stops moving before reversing its direction, so it's all GPE here. And when it has no more height, but it's going at a good velocity, its maximum velocity, it would be KE here. So now, since we're at the maximum amplitude, we're way up here, which means it has no KE. So the total energy is going to be equal to mgh. We can plug in our numbers, and we're left with total energy is 2 joules. So E tot from the last slide is 2 joules. Now they want to know what's the maximum velocity of the pendulum from the previous slide. So here we go again. E total equals KE plus GPE. Now it's going to have its maximum velocity at this point right here, where it has no height. No height, no GPE. So E tot equals 1/2 mv squared. And we're solving for velocity, maximum velocity. So we multiply both sides by 2. The half and the 2 cancel out, so we have 2 times E tot equals mv squared. Now to get rid of the m, we divide both sides by m. The m's cancel. So now we have v squared equals 2e tot over m. We don't want v squared. We want v. So we square root both sides, and we have velocity equals square root 2 times E tot over mass. Now we have our velocity isolated all by itself. Now and only now can we start plugging in our values, which is this value right here. And we get a velocity of 2 meters per second. Summarize the unit. We're done with the unit. We remember going back that period equals the time over revolutions. Frequency equals the revolutions over time. Period is equal to 1 over the frequency. and frequency is 1 over the period. When we're talking about a mass on the spring, we said it was a combination of two energies. It was a combination of EPE and KE. And here's the equations for each. We talked about the period of a mass spring is 2 pi times the square root of, remember, Michael cores, M over K. And frequency is the inverse of that, 1 over 2 pi square root cores Michael. And for a pendulum that we just discussed, the total energy is a combination of GPE and KE. And here's the equations for each. The period is equal to 2 pi the square root of L over G, which I just think of the square root of large, right? L over G. And frequency is 1 over 2 pi square root of G over L, the opposite. It's the end of our unit.